Hello, everyone, and a warm welcome to the lecture series describing chemical bonding and intermolecular forces. As usual, let me start with some fun facts. You might have heard about the lotus plant, which grows in aquatic environments. To thrive in such an environment, the surface of a lotus leaf is highly water repellent. Scientists call surfaces with this property superhydrophobic. The superhydrophobic character of a lotus leaf not only allows it to float on water, but also causes any water that falls on the leaf to bead up and roll off. The water drops collect dirt as they roll off, keeping the leaf clean, even in the muddy ponds where lotus plants tend to grow. Because of its self-cleaning properties, the lotus plant is considered a symbol of purity in many Eastern cultures. But what forces cause the lotus leaf to repel water so efficiently? Although this plant's self-cleaning nature has been known for millennia, the effect was not fully understood until the 1970s when scanning electron microscopy images revealed a rough leaf surface. The rough surface helps minimize contact between water and the leaf. Another important factor contributing to the plant's self-cleaning nature is the contrast between the molecular composition of the leaf and that of the water. The leaf is coated with hydrocarbon molecules that are held together by forces different from those that hold the water molecules together. As a result, the water molecules preferentially surround themselves with other water molecules, thereby minimizing their contact with the surface. The lotus effect has inspired scientists to design superhydrophobic surfaces for applications such as self-cleaning windows and water-repellent clothing. To understand the lotus effect and other phenomena involving liquids and solids, we must understand intermolecular forces, the forces that exist between molecules. So, from the high school, you probably know that gases consist of rapidly moving molecules, or atoms, separated by relatively large distances. In contrast, liquids and solids form the condensed phases, consisting of molecules, atoms, or ions that are in close contact with one another. The attractive forces that hold particles together in the condensed phases are called intermolecular forces. The magnitude of these intermolecular forces determines whether the particles that make up a substance are in the gas, liquid, or solid state. Earlier in this module, you encountered an example of intermolecular forces in the form of ionic bonding, where oppositely charged ions are held together by electrostatic attraction. Because the particles in an ionic compound have discrete charges, the attractive forces between them are especially strong. This is why ionic compounds are typically solids at room temperature. The intermolecular forces discussed in this module are also the result of electrostatic attractions. But these attractions involve only partial charges rather than discrete charges and are therefore weaker than the forces involved in ionic bonding. We will begin our discussion of intermolecular forces with the attractive forces that act between atoms or molecules in a pure substance. These forces are known collectively as van der Waals forces and include dipole-dipole interactions, hydrogen bonding, and dispersion forces. We should start with dipole-dipole interactions, which represent attractive forces that act between polar molecules. Recall that a diatomic molecule containing elements with significantly different electronegativities, such as hydrogen fluoride, has an unequal distribution of electron density and therefore exhibits partial charges, positive at one end and negative at the other. As a result, the partial positive charge on one molecule is attracted to the partial negative charge on a neighboring molecule. For instance, the following figure shows the orientation of polar molecules in a solid and in a liquid. As you can see, the arrangement is somewhat less orderly in the liquid than in the solid. Since this attractive force between polar molecules is coulombic, the magnitude of the attractive forces depends on the magnitude of the dipole. In general, the larger the dipole, the stronger the attractive force. Certain physical properties, such as boiling point, reflect the magnitude of intermolecular forces. So, A substance in which the particles are held together by stronger intermolecular attractions will require more energy to separate the particles and will boil at a higher temperature. The graph presented here lists several compounds with similar molar masses along with their dipole moments and boiling points, illustrating the significance of dipole-dipole interactions. Similar interactions can occur between ions and polar molecules, and in essence, these are another form of electrostatic attractions involving charged species. Ion-dipole interactions occur in mixtures of ionic and polar species, such as in an aqueous solution of sodium chloride. As you probably guessed, the magnitude of ion-dipole interactions depends on the charge and size of the ion, as well as the dipole moment and size of the polar molecule. Accordingly, cations generally interact more strongly with dipoles than anions of the same charge magnitude. The reason for this is that cations tend to be smaller than anions. The following figure illustrates the ion-dipole interaction between sodium and magnesium ions with a water molecule, which has a large dipole moment. Since the magnesium ion has a higher charge and smaller size than the sodium ion, it interacts more strongly with water molecules. We will explore this in more detail in the next module, where I will introduce you to the properties of solutions. Although the intermolecular forces discussed so far are all attractive, molecules also exert repulsive forces on one another, especially when similar charges approach each other. When two molecules approach each other closely, the repulsions between electrons and between nuclei in the molecules become significant. The magnitude of these repulsive forces rises very steeply as the distance between molecules in a condensed phase decrease. This is why liquids and solids are so hard to compress. In both liquids and solids, the molecules are already in close contact with one another and therefore greatly resist being compressed further. Now, let's briefly discuss intermolecular interactions between nonpolar molecules. You probably know that nonpolar gases, such as nitrogen and oxygen, can be liquefied under the right conditions of pressure and temperature. So nonpolar molecules must also exhibit attractive intermolecular forces. These intermolecular forces are also electrostatic in nature, as are all intermolecular forces, but they differ from other intermolecular forces because they most likely arise from the movement of electrons in nonpolar molecules. On average, the distribution of electron density in a nonpolar molecule is uniform and symmetrical, which is why a nonpolar molecule has no dipole moment. However, since electrons in a molecule have some freedom to move, the molecule may, at any given moment, have a non-uniform distribution of electron density, giving it a fleeting, temporary dipole, called an instantaneous dipole. An instantaneous dipole in one molecule can induce dipoles in neighboring molecules as the temporary partial negative charge on one molecule repels the electrons in a neighboring molecule. This repulsion polarizes the second molecule, which then acquires a temporary dipole. The molecule polarized in this way, in turn, polarizes the next molecule, and so on, leaving a collection of ordinarily nonpolar molecules with partial positive and negative charges and electrostatic attractions between them, as shown in this figure. The resulting attractive forces are called London dispersion forces, or simply dispersion forces. The magnitude of dispersion forces depends on how mobile the electrons in the molecule are. In small molecules, such as fluorine, the electrons are relatively close to the nuclei and cannot move about very freely. Thus, the electron distribution in fluorine is not easily polarized. In larger molecules, such as chlorine, the electrons are somewhat farther away from the nuclei and, therefore, move more freely. In other words, the electron density in chlorine is more easily polarized than that in fluorine, resulting in larger instantaneous dipoles, larger induced dipoles, and stronger intermolecular attractions overall. Molecules that more readily acquire an instantaneous dipole are said to be polarizable. In general, larger molecules have greater polarizability than smaller ones. The trend in the magnitude of dispersion forces with increasing molecular size is illustrated by the data in the figure on the left. You should remember that dispersion forces act not only between nonpolar molecules, but between all molecules. The last topic we should touch upon is hydrogen bonding, which is a special type of dipole-dipole interaction. What is important is that, while dipole-dipole interactions act between any polar molecules, hydrogen bonding occurs only in molecules that contain hydrogen bonded to a small, highly electronegative atom, such as nitrogen, oxygen, or fluorine. In a molecule, such as hydrogen fluoride, shown here, the fluorine atom to which hydrogen is bonded draws electron density toward itself. Being small and very electronegative, the fluorine atom draws electron density away from hydrogen very effectively. And since hydrogen has only one electron, this leaves the hydrogen nucleus practically unshielded, giving hydrogen a very large partial positive charge. This large partial positive charge is then powerfully attracted to the large partial negative charge on the small, highly electronegative fluorine atom of a neighboring molecule of hydrogen fluoride. The result is an especially strong dipole-dipole attraction. One remarkable consequence of hydrogen bonding is seen in the densities of ice and liquid water. In most substances, the molecules in the solid state are more densely packed than those in the liquid state, making the solid phase denser than the liquid phase. By contrast, the density of ice at 0 degrees Celsius is 0.917, which is less than that of liquid water at 0 degrees. Therefore, ice floats on liquid water. The lower density of ice can be understood in terms of hydrogen bonding. In ice, the water molecules assume the ordered, open arrangement shown in this figure. This arrangement optimizes hydrogen bonding between molecules, with each water molecule forming hydrogen bonds with 4 neighboring water molecules. However, these hydrogen bonds create the cavities seen in the middle image. When ice melts, the motions of the molecules cause this ordered structure to collapse. As a result, the hydrogen bonding in the liquid is more random than that in the solid, but is strong enough to hold the molecules close together. So, liquid water has a denser structure than ice, meaning that a given mass of water occupies a smaller volume than the same mass of ice. The expansion of water upon freezing is responsible for many phenomena we take for granted. It causes icebergs to float and water pipes to burst in cold weather. The lower density of ice compared to liquid water also profoundly affects life on Earth. Since ice floats, it covers the top of the water when a lake freezes, thereby insulating the water. If ice were denser than water, ice forming at the top of a lake would sink to the bottom, and the lake could freeze solid. As you might imagine, most aquatic life could not survive under these conditions. In the end, let's take a look at the following figure, which demonstrates the boiling points of the binary hydrogen compounds of groups 4 through 7. Within the series of hydrogen compounds in group 4, the boiling point increases with increasing molar mass. However, in groups 5 through 7, the smallest member of each series does not follow this trend and has an unexpectedly high boiling point. This departure from the trend in boiling points is another illustration of how powerful hydrogen bonding can be. Ammonia, hydrogen fluoride, and water have anomalously high boiling points because they exhibit strong hydrogen bonding. In contrast, methane, the smallest member of the group 4 series, does not exhibit hydrogen bonding as it does not contain an NH, OH, or FH bond. This is why it has the lowest boiling point in that group. To sum it up, in this lecture, we briefly discussed intermolecular forces, which act between molecules or between molecules and ions. Generally, these attractive forces are much weaker than bonding forces, and we typically refer to them as van der Waals forces. You saw that dipole-dipole forces and ion-dipole forces attract molecules with dipole moments to other polar molecules or ions. We also spoke about dispersion forces, which are the result of temporary dipole moments induced in ordinarily nonpolar molecules. The extent to which a dipole moment can be induced in a molecule is called its polarizability. In the end, I introduced you to hydrogen bonding, which is a relatively strong dipole-dipole interaction between a polar bond containing a hydrogen atom and an electronegative oxygen, nitrogen, or fluorine atom. Hydrogen bonding can explain some anomalies, such as high boiling points and reduced densities in certain molecules. The following figure shows how to determine which intermolecular forces are present between atoms, ions, and molecules. If ions are present, then you either have ionic bonding or ion-dipole interactions. If ions are not present, then you either have dipole-dipole interactions or dispersion forces, which operate in nonpolar molecules. Dipole-dipole interactions also include hydrogen bonding, which is present only in molecules that contain hydrogen bonded to a small, highly electronegative atom, such as nitrogen, oxygen, or fluorine. In the next module, I will introduce some important properties characteristic of liquids. You will also learn about solutions and their colligative properties. Thank you for your attention.